the understanding of difference between a one-sided and a two-sided t-test. And that's the version of the t-test that would involve, one-sided version is the one that would involve anything that's not just an equal sign, like mu1 is equal to mu2, or the alternative hypothesis, mu1 is not equal to mu1 or mu2. So let's think about this. I'm going to talk about two populations, the mean of population 1 and the mean of population 2. We don't know what the mean of population 1 is. We don't know what the mean of population 2 is. We don't know what the standard deviation of population 1 is, and we don't know what the standard deviation of population 2 is. We don't know either one of those. All we know is what happens when we sample these two populations. Okay, when we sample these two populations, we find that the mean for sample 1, let's say it's a sample of size 10. Okay, when we sample that population, the mean comes out to be, of that sample of 10 people, the mean comes out to be, let's say, comes out to be 7. When we sample the second population, which has a mean of 2, we don't know if they're the same mean or different means. X bar 2 comes out to be 9. Okay, and let's say that sample size is also 10. Doesn't really matter. Turns out standard deviation of this population happens to be, of this sample, happens to be 1. And the standard deviation of this population happens to be 2. Well, now, if we were doing a one-sided hypothesis, we would be starting with the assumption that we don't know, have any idea whether population 1 mean or population 2 mean is greater than the other. Okay, we don't have any idea. So our null hypothesis would be mu1 is equal to mu2, and our alternative hypothesis would be mu1 does not equal mu2. Okay, well, let's say that for some reason that I know that mu2, right, can only be bigger than mu1, can't possibly be smaller than mu1 for whatever reason. Maybe it's some sort of physiological effect, maybe it's physics, maybe it's the position of the sun, but I know for a fact mu1 can only be larger or equal to, right? There's always that caveat that they could be equal than mu2. And I want to say to myself, I want to prove that that's not true. I want to prove that mu1 is bigger than mu2, right? I want to prove that this starting point, this assumption that mu2 can only be bigger, is wrong, and that mu1 is in fact bigger than mu2. Okay, so I am going to take this as my null hypothesis. Okay, H null, mu1 is less than or equal to mu2. The equal part and the less than or greater than is always in the null hypothesis. The equality, the option for equality is always in the null hypothesis. H alternate is mu1 is greater than mu2, right? So what I'm doing there is I'm saying, well, if this is a distribution of all the possible sample means, I'm saying that mu1, I'm starting with the assumption that mu1 is greater than or equal to mu2. Well, I'm not worried about two tails anymore, right? Normally, I would be looking at two tails, and I would be worried about whether mu1, the difference between mu1 and mu2 is in the lower tail or in the upper tail. If the t-scores are a very large positive t-score and a very large negative t-scores, so that the distance in standard errors away from each other of these means is far enough that I'd be in the lower 2.5% or the upper 2.5%. So I would be saying that alpha is equal to 0.05, and half of that would be here and half of that would be here. Well, since I'm assuming to start off with that mu1, I'm making the assumption to start off with that mu1 is always less than mu2, and I have to prove that it's actually greater than. Well, I'm going to take that bottom part and forget about it. And I'm going to put all 5% at one end, right? So in order for this to be true, right, my t-score no longer has to be so far out that there's only 2.5% left in the upper tail. Now all 5% can be in the upper tail. So my t can be smaller. The distance between these two means can be smaller, right, and still reject the null hypothesis. Well, you have to give me the whole. Now you got to give me the whole thing. In other words, if the question is, if we want to show that mu1, we want to show that mu1 is greater than mu2, right? Then that would be our alternative. We want to prove that mu1 is bigger than mu2. Then mu1 greater than mu2 is our alternative hypothesis. Our null hypothesis is that that's not true, or they're equal, right? So that's the way that I would look at it. And let me go ahead and actually do this problem, okay? What if it says different? We're just going to use this, and we're going to split the 2.5%, the 5% between either end, and use that t-score. We know the population standard deviation is a very large sample size, that would be 1.96, and negative 1.96 would be the critical values for us, or a little bit bigger if it's a t-score, right? In this case, these are small sample sizes. Okay, so now notice, next thing I have to think about is we had two different formulas, right? This formula that I have right here, let me see if I can't get it to stretch out. Whoops. I think I have to switch to a pointer. Let me see if I can do it this way. Yeah, I think I can get, I think I can grab the whole thing. Okay, this formula represents the formula if the variances are not equal, right? If we're starting with the assumptions that the variances are unequal. Okay, so now I'm going to use that assumption because I'm looking at the standard deviations of these two samples, and one is double the other. So I'm going to say let's stick with unequal variances. There's a different formula that we use for equal variances. I'll talk about that in a few minutes. The formula that we would use for equal variances includes a calculation for a pooled standard deviation. Now, we did a problem very similar to this in class. I think we did one problem in the lecture. We repeated a problem very similar to it in the lab, and we're going to just run through the numbers on this pretty quickly so that we can see how it actually works out and how we apply this idea of a one-tailed test. Now, we all agree now that this is a one-tailed test. This is our null and our alternative hypothesis. And if I'm lucky, I'll prove that mu1 is bigger than mu2. Okay, so mu1, well, actually, to tell you the truth, I made a mistake there right off the bat, didn't I? Right? Because mu1, the standard deviation for the sample mean that I got from mu1 is 7, and the sample mean that the x bar I got from mu2 is 9. So there's no way that I'm going to be able to prove using this data that this population is greater than that one. So I'm going to reverse these two numbers, right? So it has a shot of working, right? The other way around, never have a shot of working, right? Because our sample says, even our samples came out bigger. Now at least it has a shot, and it's just a matter of the variability is small enough that, like, we have a chance to actually reject the null hypothesis that they're far enough apart. Okay, so now let's take a look at this. Let's actually go ahead and calculate this. Okay, so now one of the things that we're going to need to complete this formula is that we're going to need the standard error, the bottom half of this t equation. And I'm going to have to calculate that. And that's calculated from the square root of the standard deviation of 1 squared, that's the variance of 1, over the sample size of 1, plus the standard deviation of the second group squared over the sample size 2. So in this case, it's going to be the square root of 1 squared over 10 plus 2 squared over 10. Kind of simple numbers that we managed to find for ourselves, fortunately. So 1 squared over 10 is 1 over 10. plus 2 squared over 10. 2 squared is 4 over 10. It's 4 over 10. So we got really lucky here, right? We can combine, if these weren't the same denominators here, we would have to convert them into decimal fractions, add them together. But in this case, I can see it's 5 over 10, or 0.5, right? But we still have to take the square root of that 0.5. Okay, what's the square root of 0.5? What number multiplied by itself will give us 0.5? So I'm going to take up my calculator, put in 0.5, find the square root of it, and it turns out it's 0.71. Okay, so that's equal to 0.71. That is our standard error. Okay, so now my t-score is equal to the difference between these two means, 9 x bar 1 minus x bar 2 over the standard error, or in other words, 9 minus 7 over 0.71. Okay, so that's going to be equal to, let's see what that's equal to. That's equal to, that is equal to 2 over 0.71, which is equal to a t-score, or number of standard errors apart, of 2 divided by 0.71 is equal to 2.82, I'll call it. 2.82. Okay, 2.82. Okay, assuming that our acceptable level of error, alpha, is equal to 0.05, what do I do with this t-score now to decide whether I can reject my null hypothesis and accept my alternative hypothesis? Somebody want to hazard a guess at what I do next? What do I have to look up? Well, my t-score is 2.82. We have to find t-critical. Thank you very much. Okay, t-critical. Oops, t-table. We'll open our t-table from Agresti. Here's our t-table. Okay, so remember now that our, I closed the wrong one. Let me try this again. T-table. Okay, here we go. Okay, here's our t-distributions. Okay, so now I want a 5% chance of being wrong in a single tail test. Which column should I use? The first, the second, the third, the fourth, the fifth, or the sixth? Any opinions? One opinion is the third, right? Okay, any others? I got most people want you to use the second. Okay, exactly, good, thank you, Jenny, you caught it, right? Okay, if this were a one-tail test, a two-tail test, my 5% would be divided up between these two ends, okay? And I would use the middle column, my 2.5% in each tail to add up to my 5%. Well, since it's a one-tail test, all 5% is in one tail, whether it's the right one or the left one, it's in one tail. So I use this one. So now how many degrees of freedom do I have? Well, that's kind of going to get nasty now. See this formula here? This is the formula that we use when we have unequal variances for the degrees of freedom. It was pretty simple calculating our standard error, but unfortunately there's a trade-off there. And that trade-off is that when we go, I'm having a hard time grabbing this thing. I want to make it bigger so you can actually see it. There we go. Oh, you know what it is? There's so many other objects around it now. I think I got it now. There it is. There's our formula. So I can grab this other stuff, get it out of the way. Okay, I think we can almost see it now. Okay, actually I pulled that out of there. Okay, so now here's our formula. This is a pretty difficult formula for us to work out on the fly, right? So what I'm going to do is, instead of attempting to calculate this formula, I'm going to take a conservative approach. I'm going to say the degrees of freedom is equal to the sample size for the smaller sample. In this case, they're both the same size, so they're both 10. So I take 10 and subtract 1 from it and say that the degrees of freedom are equal to 9. Alternatively, if you have the time to do it, you would use this formula to actually calculate the degrees of freedom. Somebody has time later on, they might want to give it a try for this example and see what number you come up with. But I'm going to use 9 instead. Okay, so let's look up what the 9 degrees of freedom is going to be for our one-tailed test. Our T critical is going to be 1.833. So, do I exceed my T critical with 2.82? I do. Are these two means far enough apart, given the variability in the sample, far enough apart for me to reject my null hypothesis, which was, if I can drag it back in here again, I may not be able to get it back in here again, which was, I'll rewrite it because I think it's relevant here. Right? H null is mu 1 is less than or equal to mu 2. Like, okay. So my T score is greater than my critical value of T, so I can reject my null hypothesis and accept my alternative hypothesis. That indeed it's not an accident that the sample 1 had a mean of 9 and sample 2 had a mean of 7. That indeed the means for the two populations are probably, with at least 95% certainty or 5% chance of being wrong, that they're probably different as well. The actual means of the populations, mu1 is greater than mu2, right? That we know that with less than 5% chance of being wrong. We don't really know it, but we know with that level of uncertainty. Why I'm using 9 because it's difficult for me to calculate by hand this calculation for degrees of freedom. You could do it, and you'll get the number that you should be using for degrees of freedom. However, I don't want to kill all that time right now. So what I'm doing is I'm saying, instead of using this formula, I'm going to use a very conservative approach. In other words, it'd be hard for me. The real degrees of freedom are certainly larger than this number and would give me a better chance of rejecting the null hypothesis. I don't need it here. Look, my T-score is so big, I know I'm not going to need it anyway. So I'm going to use a simple approach and say that it's just going to take the smaller of the two samples, sample size smaller of the two sample sizes, subtract 1, sample size minus 1, degrees of freedom, subtract 1, get 9, right? Sample size is 10, get 9, and use that as my degrees of freedom. If I failed to reject the null hypothesis, remember, the bigger the sample size is, the smaller my T can be to reject the null hypothesis, the smaller my critical T. In this case, I didn't need it to be any smaller, so I could use that simplification of the degrees of freedom. You know, I didn't need the degrees of freedom to be 11 or 12 or 13, right? 9 was good enough. I'm able to reject it at that level, so I know if I work it out for the actual number of degrees of freedom, they're going to be a bigger number. So I'm even more certain, you know, it's even easier for me to reject it, but I really don't need it because I've already rejected it. But what if it's different for the two samples? Just go with the lower number. Yes, exactly. We want to take a conservative approach, right? So if the sample size for this was 10, the sample size for this was 20, it would be then you work this formula out, it's going to be somewhere in between most likely, right? So if you were to say 20 minus 1 is 19, you'd kind of be cheating a bit there. You'd be giving yourself an unfair advantage. But if you take 10 minus 1, the smaller sample size, and use that for the degrees of freedom, you're actually giving yourself a disadvantage at the worst. At the best, you're giving yourself a disadvantage. So you're not really cheating. And if you manage to reject the null hypothesis at that level, well, all well and good, you're done. But if you didn't, and it was very close, then maybe you would go back and do this actual very rigorous calculation to find out what it really is. I most likely will not ask you to calculate. I'll tell you something like, use smaller sample size minus 1 as your degrees of freedom if you see a problem like this on here, or maybe I'll just give you the degrees of freedom or something like that. But I wouldn't ask you on a test to bother to do that. Okay, so now let me get new problem here. New. Oops, I don't want that. I want a new page. New page. Okay, and I just want to see quickly if I can find a formula. Okay, equal t-test equal variance. Okay, it's tough for me to draw these formulas out, so I'm hoping to find one that Oh, here we go. Let's see if I got that there. Okay, so here is what formulas that we would use if we were to work with and assume equal variances. Okay, well, let's take a look at what we have here. They use y1 and y2. The difference is assumed to be 0 to start off with, right? So this just drops out. It's really just a placeholder. So the mean of sample 1 minus the mean of sample 2, just as we did before, except the standard error now. The standard error is equal to, let me see what the standard error is equal to. Well, gee, it's equal to this number called the pooled standard deviation. Well, how do you calculate the pooled standard deviation? Well, you use this formula to calculate it. This is an interim step. You actually use n minus 1 times the standard deviation of population of sample 1 squared plus n2 minus 1 population of sample 2 squared over n1 plus n2 minus 2. You would use that for your pooled standard deviation, calculate that number, plug it in here, multiply it times the square root of 1 over the sample size of the first group plus the sample size of the second group, right? And then we would say, oh, well, gee, we'd calculate this t-score, and then we would say that our degrees of freedom are n1 plus n2 minus 2. The sum of the two sample sizes minus 2. In other words, in the case we just had, 20 minus 2 or 18. Okay, so funny thing about this one is when we assume equal variances, right, what happens? We wind up getting a very simple calculation for the degrees of freedom, but then we get a complicated calculation for the standard error, or standard deviation and standard error, the pooled standard deviation and standard error. And the reason why you're doing this is because since you think they're close enough to assume equal variances, you would just then say, well, if the variance of this one is 1.9 and the variance of this one is 1.8, maybe I can just combine these two so that I'm instead of looking at them as two separate populations, I use both of them together to calculate an overall standard deviation, which is a more accurate approximation of the population standard deviations. Okay, assuming that the two populations, even though they might have different means, would have similar or equal standard deviation. So you get a little bit of an advantage there. Remember, this one is, let me write it down. And let's do this one now with that in mind. Okay, this is for equal variances assumed. Okay, I use S squared for equal variance because technically that's the variance is the standard deviation squared because you calculate it by taking the variance by the square root of it, right? So I use that to represent, but you could also just say equal stand. If you say equal variance, you're basically saying equal standard deviations also. Let's take the same problem. This time y1 is equal to y bar 1. I'm going to call it x bar 1. Again, just like we did before, that's equal to 9. X bar 2 is equal to 7. The standard deviation of this first one. Well, I'm going to do something here. I'm going to make them equal. I'm going to say this one's 1.5. I'll say the standard deviation here is 1.5. Okay. And, but, usually they won't be exactly equal. This might be 1.4 or 1.6, but they're close enough that you might say, gee, I have a strong argument that they're equal. I'll say the sample size here is 10, just like before, and the sample size here is 10, just like before. Okay, so I'm going to calculate my t-score, right? My t-score is going to be equal to, let's see, it's going to be equal to x bar 1 minus x bar 2 divided by the, let's see, this value down here. I'm just right now going to call it standard error, right? So now I have to calculate what this is, right? So the first thing I need is the pooled standard deviation. Okay, so let's calculate our S square pooled. Okay, that's going to be equal to, let's see, N1 is 10 minus 1 times S1 squared. Well, 1.5, that's 1 and 2. 1.5 squared is 15 times 15 is what, 225? Is that right? 2.25? Am I right? Yeah, I'm having brain freeze here. Let me use this. Clear. 1.5 times 1.5 equals 2.25. I had it right. What do you know? 2.25. This is times 2.25, right? Plus, and 2 minus 1, that's also, sample size happened to be 10. So that's also going to be 9 times 2.25. That's 2 squared. That's 2 is the same. Won't always be exactly the same. Might be slightly different, but you get the idea. Divided by n1 plus n2 minus 2, and that's 18. So the pooled standard deviation squared, the variance, pooled variance, is equal to 9 times 2.25 plus 9 times 2.25. Okay, now normally I'd factor this, multiply, add these together to, add them to call it 4.5 multiplied by 9, because I can pull out the nines and so on and so forth, factor them out. I'm not going to do that because I don't want to cause a riot. Okay, yes, isn't there some way to generate the t-score in SPSS so we don't have to do all these calculations? Yes, if I'm going to ask you to do, if I'm going to ask you to calculate it in SPSS, I'm going to give you the raw data. If I want you to do it this way, I'll give you the data this way. We haven't really looked at using SPSS, using what you would call using summarized data. In other words, just the mean and the standard deviation. We haven't looked at that yet. So maybe we may get to that in a little while, because some of ours may be valuable for some of us on our projects and stuff like that, if we can find easier, better ways to do that. But yeah, if you have the raw data, you can go ahead and use SPSS. But for this exam, if you don't have the raw data and I just give you the numbers, you should use the formulas or use Excel or your calculator and so on and so forth. I'll try not to make it very complicated. Okay, so anyway, okay, S squared pooled is going to be equal to, well, let's calculate this. 9, where's my calculator? Is going to be, where'd it go? What happened? I clicked it. There it is. Clear, let's clear it. Let's see, 9 times 2.25 is equal to this, and I'm going to multiply it by itself. Okay, it's equal to, I shouldn't have done that. I was supposed to add them. Clear. Excuse me. Where was I? 2.25 times 9. Okay, and then I have to do it again there and add them together, right? Plus is equal to 40.5 added to itself. So that's the whole top part of this, and divided by 18 is equal to 2.25. Well, that worked out pretty easily, right? Okay, so now this is equal to 2.25. However, notice that this is for the pooled variance, not the pooled standard deviation. So if I want to know S pooled, which is what I really need here, right? If I know S pool, I got to take the square root of that 2.25. And that square root of that 2.25, right? Well, what a coincidence. It's 1.5. I worked out some good numbers here, right? And that was on the fly, too. Okay, so S pooled is equal to 1.5. Okay, this was all like, you could call it luck, but I like to think that, like, I chose these numbers carefully and they came out nice and easy. Why is the equal variance formula more complicated than the unequal variance formula? Without doing the derivation, that would be hard for me to explain. That's a good question. It's not really in the equal variance is assumed. We're going through an extra step to give us a bit of an advantage of taking advantage of an assumption that both populations have the same variability, and then combining those numbers rather than depending on one and the other's different values, combining those two numbers so I get a single standard deviation for both populations that's more accurate than if I had just sampled one and sampled the other separately and assumed that they were different. But the trade-off of that is, when we do that, is it gets a bit more complicated to calculate that standard deviation. We have to kind of find a weighted average kind of for that standard deviation, and so if this had been 1.5 and this had been 2, we would have found something in between as the pooled standard deviation. Okay. On the other hand, if we did it the other way, the calculation is pretty simple because we're assuming they're different. But then it's a little more complicated calculating the number of degrees of freedom. But I don't want to go too far into that. But part of it is part of the explanation is buried in the derivation of all this. And maybe at some point that we'll be able to look at it in a little bit more depth. Okay, so let's finish this up. Okay, so now I'm going to figure out my t-scores. My t-score is equal to 9 minus 7 over my standard error. Well, this is my pooled standard deviation, but I still haven't found out my standard error. My standard error is S pooled times the square root of 1 over N1 plus 1 over N2. I'm going to see if I can online find a video where somebody has explained that, or maybe if I get some time, which I'll tell you, time is tough to come by in the summer session. If I get some time, maybe I'll put something together that makes some kind of sense. I already promised you before the end of the semester a video on Bayes' theorem. I haven't forgotten that. I will do something on that. So 9 minus 7 is 2 over the pooled standard deviation is 1.5 times 1 over 10 plus 1 over 10. Okay, and I'm taking the square root of that 1 over 10 plus 1 over 10. So that's equal. Don't forget the square. These are buried in square roots. It's very easy to do this inner calculation and to forget to take the square root. In fact, we did that when we were in class once, right? And we didn't realize it until the very end of the class. Okay, so pool standard is 2 over 1.5 times, and what is 1 over, that's 2 over 10, which is 0.2, and I have to take square root of 0.2. Let's calculate that. I think it's 0.141. Let's see, clear root. Square root 2, the 0.2. 0.2 is the square root. It's 1.48, I'll call it. Oh, that doesn't seem right, does it? That's wrong. Try that again. Okay, 0.2, take the square root of 0.2, it's 0.45. It always helps to kind of keep an eye on what you're actually doing. Okay, so my t-score in this case is going to be 2 divided by 1.5. 1.5 times 0.45 equals 0.67. I'm going to put that into memory and clear this. And I'm going to take 2 and divide it by my result, which was 0.67. Oh no, I screwed that up. Okay, 0.675. Is that still there? Yeah, that's still there. I'm going to clear that. Okay, 2 divided by, I'm going to recall that, and that's equal to, it's equal to 2.96. 2.96 is my t-score, assuming equal variances. Now remember, the difference here is that I changed the standard deviation, I changed the variability in these two so that they were equal. Otherwise, it's the same example that I did before, right? In which I found that 2.82. It didn't make that much of a difference, did it? Right? And in fact, when you look at if I had done this with with 1 and 2 and equal variance is assumed, I think you would have gotten a slightly bigger difference in the t-score. SPSS, we know that this is going to work out no matter what it does. We'll work it out in SPSS anyway. Okay, so my t-score is 2.96. Well, now I'm going to give you two options. One option is my null hypothesis and my alternative hypothesis. The first one is mu1 equals mu2. Okay, and alternative hypothesis is mu1 does not equal mu2. Okay, so now I have to go to my t-table. Okay, it's back here, I think. Here it is. Here's my t-table. I'm going to go to my t-table here, and I'm going to say, okay, Well, that is, what kind of test is that? That's now a two-sided test, right? So, did I do something wrong there? Square root 2.2 minus 6.7. Did I? Oh, okay, no problem. I think we're okay, right? I fell behind on the comments there a little bit, but you saw me caught me making an error there, and a couple of you guys tried to correct me there, but I think I caught it. Okay, so now it's a two-sided test. So which column, if my alpha is equal to 0.05, which column am I using now? Well, two-sided test, I'm going to use this side. Half of my 5% is in each tail, so 2.5% in each tail. So my t-score, my critical t-score, is going to be, what did I say my degrees of freedom are going to be for this kind of test where I assume equal variances? It's going to be the two sample sizes added together minus 2, right? 10 plus 10, 20 minus 2. So it'd be 18 degrees of freedom. You guys still there? Comments have stopped, so I'm worried that like maybe I'm not talking to you guys. Okay, good. So 18 degrees of freedom. So my T critical is going to be 2.1. Okay, do I exceed 2.1? I do exceed 2.1, so I can reject my null hypothesis and accept my alternative hypothesis. Notice that my T critical was 2.1, where before, in a very similar example, which was one-sided, my T critical was very small. It was like 1.87 or something like, right? Remember this one was 1.87 or something like that. A two-sided test gives you a T critical that's a bigger number. So that means the difference between your two means has to be bigger, have to be further apart in order to reject your null hypothesis. I got 18 degrees of freedom. I added up sample size one, N1 and N2. They were each 10, so it's 20, minus 2 for two groups, right? So it's 18 minus 2 is 20 minus 2, which is 18 degrees of freedom. Okay? So now I'm going to take another look at this now. Let's say that, the mean here that I got was 9 and x2 was 7, right? Let's say for some reason I know that x1 can't possibly be smaller than x2, right? So, excuse me. Let's say that it can't possibly be smaller than x2, but I want to prove that x1 is larger than x2. But I don't want to do a two-sided test. I only want to do a one-sided test. In other words, I want to get an advantage here and make it easier for me to prove that mu1 is bigger than mu2, right? So that's really what I want to prove, is that mu1 is bigger than mu2. So if that's what I want to prove, that's what's going to wind up in my alternative hypothesis, right? That's what I'm using this whole thing to prove, right? So my null hypothesis is that, no, they're equal, or maybe it's the other way. My null hypothesis is mu1 is equal to mu2, or it also could be less than mu2. Since we're doing a one-sided test, and since I know for some reason that's completely disconnected from the statistics, I know for some reason that mu1 can't be less than mu2. Well, that's almost a given anyway, but I'm putting it into my formula anyway. So, because I need to cover all the possibilities. The equal and the less than are in the null hypothesis. The greater than is in the alternative hypothesis. So now, if I'm doing a one-sided test, exactly all the same numbers are exactly the same. Nothing has changed here, say, except for the null and alternative hypothesis. Now I'm doing a one-sided test, alpha equals 0.05. So instead of using the third column, I use the second column. And if I go to 18 degrees of freedom, now the only thing I need, T is much smaller now, it's 1.734. So all I need to exceed my T critical is 1.7, whatever it was, 1.7 something. Well, I got a T of 2.96. It was even easier to exceed than the 2.1 for my double-sided test, right? And that's always the case. Single-sided test is a less rigorous test. It's an easier test to prove In other words, to reject the null hypothesis and accept the alternative hypothesis. Okay. Okay. I'm gonna upload this later on tonight. It's gonna, unfortunately, as soon as I get done here, I have to run away from the computer. I'll probably be back about, sadly, about 10 o'clock or so. It'll take me about 15, 20 minutes to get it uploaded. So by about 11, it should be online. Okay, I'm sorry I can't get it up sooner than that, but unfortunately, I'm really constrained in time. I have a couple of appointments this evening. Okay, so at any rate, so that's where we stand if we do this test using our calculations, depending on whether it's an equal standard deviation assumed, the equal variance assumed, or unequal variance assumed in these two populations. Okay, so now I will tell usually, if somebody were going to ask me, how would you assume whether it's equal variance or unequal variances? And I've heard various descriptions of how you might make that assumption from there are mathematical tests you can do, or from kind of like a fly by the seat of your pants kind of method. I've heard a lot of people say, well, if one is 50% more than the other, or if one is double the other, then assume unequal variances, right? But there's really more appropriate tests for that. ANOVA analysis of variance will be very simple. It might be something simple like I might print out the tables, the result tables, and ask you to make some conclusions based on the result tables. If you look at the video from last night, the second half of class from last night, it should help you out on that. Okay, so now let's say you get a similar problem to this, but you get a data set that's appropriate for SPSS. Now, I cross my fingers every time I start up SPSS because my license expired on July 1st, and it's going to be really tough for me to find somebody in ICIT on 68th Street to give me the new license. I don't know how easy I can get somebody in the summer, and it keeps coming up with a warning for me. But it eventually, so far, lets me continue running it. And I went online and I Googled around, and most people say it'll run for. In fact, I think it's got a warning back there somewhere right now. Let me close this, get this out of the way. Let's see if I can't get this open. I think I got a window open back there warning me about something. Yeah, license is about to expire. How about that nasty icon? With a big red thing over there. Oh, geez. Okay, so at any rate, thus far it's let me open SPSS, and I think it probably will until the end of the month. Hopefully, see now it's locked me out right now, but usually what happens if I restart it a second time, it'll let me in. Okay, or if I start from a file. Come on, be good to me. Okay, it's doing the same thing to me. I know there's a shot that I'll get in here. Okay, maybe now. Oh, okay, there we go. Now it's working. Okay, let me find a file here. And I think I had something in here. Let's see what we got here. That was, yeah, we did this the other night, right? Hourly wage data, hospital and employees. Okay, I'm just going to do that quickly again so you can see what the table looks like on the output. Analyze, descriptive statistics, compare means. It's going to be independent samples t-tests, right? They're independent samples, hospital workers, office workers, and not paired samples where, we did something and, we did an intervention and we measured before and after. These are independent samples. Okay, and I'm going to put in the hourly weight, and I'm going to put in the nursing type into here. Ask me to define them. Anybody remember what it was? Was it 1 and 2 or 0 and 1? I think it was 1 and 2. Okay, and I'm going to say okay. It'll do the calculation for me. If I got it wrong, I think I got it wrong, didn't I? Yep, must have been 0 and 1. I'll do it again. Analyze, compare means, independent samples, t-tests. I could have looked it up if I went into the variables view, except this time I'm going to change this, and I'm going to define the groups as 0 and 1. Doesn't matter which one I put first. And say OK. It worked that time. Okay, so it compared the hourly salary to this group, 966 people, to this group, 1,945 people. One was 1868 an hour mean, the other was 2067 average. Big samples like this, you don't need much difference in the mean to be able to say that they're different. A lot of times, like let's say this came out to be $19.50 and this came out to be $19.99. But it's only, 25 cents an hour difference, just because it's statistically significantly different. You can say with 95% certainty that they're different, doesn't mean that it's, makes a difference in the real world. They're different enough to, care about it. Okay, but this, I guess, is $2 an hour. I guess if you're making that range of money, is that's 10% of your salary. One's making 10% more than the other, so I'm going to go with that. So now this is what my output looks like when I'm done. My independent sample t-test output looks like. Let's read this. First thing I have to do is, are the standard deviations here the same or are they different? Well, this one is, it's quite a bit of difference here. I mean, look at the standard error. One is almost double the other. This one, the standard deviation is like 50%, more than 50% greater than for the hospital workers. So I'm thinking maybe these variances are not equal. Okay, so, but I'm not going to leave it up to my own judgment. I'm going to let SPSS figure that out for me. And the way I do this is I go over here and I look at, it gives me two results. It does the problem for me twice. See here, it does the problem once here on this line, repeats the same problem down here. In the first part, the top part, it assumes that the variances are equal. In the bottom part, it assumes that the variances are not equal. And it uses the same formula you would have done to actually calculate this, like pooled standard deviation or not, degrees of freedom, how to calculate it, and so on and so forth. But the way that it decides whether or not to use the top line or the bottom line, or to aid you in deciding, it first does a separate test, which is in these first 4 boxes here, or 5 boxes here. It's called the Levene's test for equality of the variances. Okay, so it comes up with a statistic called F. Has nothing, it's not F like for analysis of variance. Okay, it comes up with a statistic F. Okay, now F has a distribution associated with a probability. So if F is big enough that the probability of being wrong, if you reject the null hypothesis about the equality of the variances, if it's less than 5% chance of being wrong, and in this case, the probability of being wrong, the p-value or significance, is less than 1/10 of 1%. So this is less than 0.05 or less than 5% chance of being wrong. So we would reject the assumption, the null hypothesis for the equality of the variances. And what is the null hypothesis always going to be? The null hypothesis is that things are equal almost always, right? So in other words, this suggests, and this is less than 0.05, this suggests reject the idea that the equal variances are assumed and use the alternative that equal variances should not be assumed. So in this case, we're going to use the bottom line, not the top line. If this number here, the significance had been bigger than 0.05, right, then we would have said, oh, there's too big a chance for us to make an error if I reject the null hypothesis, because the probability of making an error is greater than 0.05, right? So then I would stick with the top line and not use the alternative equal variances not assumed. So I'm going with the bottom line. Okay, bottom line says the t-score is minus 11. That just is a function of which side, whether x1 was big, that would have been the opposite if I had made the office workers group 1 and the other group 0 versus one group 0 and the other group 1. If we had the variables defined the other way would have been a positive number. So it really doesn't matter whether that's positive or negative. We're only interested, just as we were before, in the size of that number. Okay, so this is the degrees of freedom, and they're calculated differently. Look at this one over here. We equal variance is assumed. All they did was add these two numbers together and subtract 2. That's it. That's how they got that number. With equal variance is not assumed, they had to go through that torturous calculation to get this number here. What would we have done to avoid that? We would have said take the lower number here, N966, subtract 1 from it, and call it 965, 2 degrees of freedom, right? Way below the 1538, but high enough that, it'd work for us anyway because the t-score is plenty big. Okay, so what's the significance? What's the probability of being wrong if we reject the null hypothesis? Well, that's given by our p-value, by our significance, in this case, two-tailed. And the probability is less than 0.1%. So we would reject the null hypothesis and accept the alternative hypothesis that there is a difference in the hourly salary for the population of all office nurses versus all hospital nurses. Okay, so this is the way we would use this box. Just for clarity, they also calculate a 95% confidence interval for the difference between the nurses' wages and the hospital wages. Now, we would have expected, if the null hypothesis were true, that they made the same, their salaries were the same, we would expect that the difference between these two means is equal to 0. Well, in fact, it calculated that the difference between those two means is probably somewhere. The mean difference is about negative 1.99. It's about $2 an hour is the difference, right? And it says, well, that's what we count. That's what we estimate the mean difference is. But we calculate also a confidence interval, 95% confidence interval for the true difference, not either mean, but the difference between the two of them. And the 95% confidence interval says that office nurses are making somewhere between, with 95% certainty, somewhere between $1.66 and $2.31 less than hospital nurses, right? They're both negative numbers. What that negative 1.66 to negative 2.31, what important number is not within that range? Anybody want to tell me what important number is not within that range? 0 difference is not within that range. Thank you, Michelle. Very good. 0 difference is not within that range. More evidence that the difference is different than 0 with 95% certainty, which reinforces our opinion that the actual means for the populations are different as well. So we get all that information from this table, right? Okay, so that's it. I'll post this up later on. Again, if you keep emailing me and stuff like that, I'll try and answer as many of the emails as I possibly can. It's tough to keep up with them, trust me. And I'll post answers to, later on tonight, I'll post answers to homework 3B, so you have those answers, because I haven't had a chance I actually haven't posted a practice test. I haven't had really time to actually even complete putting together the real test yet. But I think you have a pretty good idea of what's going to be there from the homeworks and from some of this other stuff that we've gone over in these various calculations that we've done. Plus the stuff that's really a curveball. It's tough to show in a practice test anyway. So, there might be a couple of problems that test your understanding a little bit better than a little bit more thoroughly than on the last exam, because we're getting into some more complicated stuff here. Analysis of variance, as I said, if it's on there, I'm probably not going to ask you to do the calculation using SPSS, but I might give you the table and ask you to interpret the table, the output from SPSS. Okay, and if I did give you an analysis of variance for you to generate your own table, it would be really simple, and I make the instructions pretty specific. But I think you should, if you needed to, you could do it for the t-test, make your own table and make your own conclusions, or do it mathematically. But the analysis of variance, since it's our first shot at it, I'll stick with discuss, maybe giving you the output and having you answer a couple of questions based on the output.